Our problem here is to solve the non-homogeneous differential equations. The second derivative of y with respect to x minus 5y equal to x squared, subject to the boundary conditions. Y of 0 is equal to 2 and y of 10 is equal to 1. By Mathematica, so this is our solution by Mathematica. And our plot here is this one, right? So we have the boundary condition here, I sub 0 equals to 2 and y sub 10 is equal to 1. So our step size here is 9 minus 1 equal to 9 minus 1 divided by 9 minus 1 is equal to 1. So our boundary condition, first boundary condition is I sub 0 equal to 2 here. And the last boundary condition is I sub 10 equal to 1. So we don't include the boundary condition here in our set of equations. Okay, so from Taylor's approximation here, so we have the y sub I sub 1 minus 2y sub I plus y sub I minus 1 over h squared minus 5yi equal to x square of x sub I. Now for the step size h equal to 1 here, then y sub I minus 1 minus 7y sub I plus y sub I sub 1 is equal to square of x sub I. Right. Then for I equal to 1, y sub 0 minus 7y sub 1 plus y sub 2 is equal to square of x sub 1. So the first boundary condition here is y sub 0 is equal to 2 here. So we substitute the boundary conditions here. Y sub 0 is equal to 2. Okay. So what we have now is 2 minus 7 y sub I plus y sub 2 equal to square of 1. So by simplifying, we have here negative 7y sub 1 plus y sub 2 is equal to negative 1. For I equal to 2, we have the corresponding differential equation here. So the corresponding approximation here. So this one. For I equal to 2 here, so we have y sub 1 minus 7, y sub 2 plus y sub 3 equal to the square of x sub 2. That's what equal x equal to 4 here because x sub 2 here is equal to 2. So 3 squared is equal to 4. So our last equation is for y sub 10 equal to 1 here. So our y sub 10 equal to 1 is our last boundary conditions. So our last equation here is y sub 8 minus 7, y sub 9 plus y sub 10 equal to the square of x sub 9. So y sub 10 is equal to 1 here. So we substitute here, y sub 10 is equal to 1. So by simplifying, we have y sub 8 minus 7, y sub 9 equal to 80. So we have here the y, we have the y's x sub 9 is equal to 9. So 9 times 9 is equal to 81 here. So 81 minus 1 equal to 80. So we have the 9 variables here: y sub 1, y sub 2, y sub 3, y sub 4, y sub 5, y sub 6, y sub 7, y sub 8, and y sub 9. Okay. So by using the Mathematica here, so we have the set of equation here. So we have 9 variables, so we have also 9 equations here. So our equation here, this is the first boundary condition, y sub 0 is equal to 2. And the last boundary condition here, we have equal to 1 here, right? So this is x sub 9. So x sub 9 is equal to 9. 9 times 9 equal to 81 here. Okay, so by entering this one, so we have the solution here. And let's line plot the solution here. Okay, so this is the approximate solution. Okay. Now our solutions becomes more accurate if the step size is, for example, 10 minus 0 all over 101 minus 1 is equal to 0.1, where y sub 0 here is equal to 2. So this is our first boundary conditions. And the last boundary condition, y sub 101 equal to 1. Right? So in our example here, we group the y sub I plus 1 and y sub I plus 1 and y sub I and y sub I minus 1. So by grouping here, we have this expression. And for here, our step size here is equal to 0.1. So h is equal to 0.1. Then let us substitute this h equal to 0.1 here. Let us substitute here in our approximating uh, differential equations. Okay, so we have this equation now. Now from that, we can now assign I sub 1 equal to 1 here. So for I equal to 1, so this becomes y sub 0 minus 2.05 I sub 0. Then 0 plus 1 is equal to y sub 1. So our x here, x sub 1 is equal to 1 here. So the square of that is equal to 1. So the number of equation is 100. That is from equation 2 minus 2.0. So it is equal. It should be equal to 2.05, and this one is equal to 0.01, where x sub 1 is equal to 1 and y sub 0 is equal to 2 here. Okay. So from this equation to the last equation here, so this is our last equation, y sub 99 minus 2.05 sub 100 plus 1. So this is the last boundary condition equal to 0.01 squared x squared of x 100. So x sub 100 is equal to 100 here. Okay, so let us use the Mathematica now in writing all the equation here. So this is our equations. And let us solve all the equations here using the end solve of the Mathematica here. So we have this. Okay, so we have the solution now of all of y sub 1 up to y sub 100 here. Okay. Then we have the list line plot of all the solutions here. So copy paste all the solutions here. So what we have here is the list line plot. So our list line plot here looks like the solutions of Mathematica here. So this is the solution by Mathematica. So this the more accurate solutions of Mathematica. So our solution by finite difference method is closer to the solution, to the approximate solution by Mathematica here. Okay. Now copy again all the solutions here, and that is equal to D. And we can use the cubic fit and the quadratic fit here, this one. So we have the quadratic fit and cubic fit here. Then let us plot the quadratic fit and the cubic fit here. Okay. So the approximation is not good here. So as you can see, so it is it it does not look like the solution by Mathematica. Okay. Now, the next step is to convert your data to CSV file extension, then to Microsoft Excel here. So you write the solution. The first solution here is equal to 2, so that corresponds to 1. The next solution here is negative 0.199. So this corresponds to the second solution here. So this one. Okay. Now the third solution corresponds to negative 2.399. The fourth solution corresponds to uh, the solution negative 4.67. All right. So up to the 101 solution here. The next, so we have the last equation, the last boundary condition corresponds to 1 here. Okay. Then write so this is equal to E. So right here, export the data CSV. So we have this one. So data dot CSV. Then after that, uh, write the directory here. So this is a directory. So the directory can give you the location of the data CSV here. Okay. So it can be found in your uh, C drive here, users the tabular. Then if you open that, that is already an Excel. So it is like you are opening an Excel file here. So after you have an Excel here, uh, you go to the chart. So you plot now all the points here. So this is what you will have. The X and Y data points. And then graph that. So we have the equation here. So equation from Excel here. So it looks like this one, the plot. And so on the upper right side of the plot, click the plus sign, plus, then click the trend line options, polynomial of order 6, then click the display equation here. So here you have the trend line, then click the polynomial of order 6 here. Then display the equations. So you have the equation here. Okay. Now you can now plot the equation, the given equation here from the Excel. So it looks like this. So it looks like the equation given by the Mathematica. Okay. But here the approximation of the solution here is given by Mathematica. But the data points in our solutions is our final solution here. Okay.